Hi year 8, this is the fourth video actually I'm making today, but I'll be making 4 more, so you're in for another treat. And this is one of my favorite experiments ever since I've started teaching. Always loved making pure salts, and the blue crystals that you always see with associated with chemistry. I've tweeted so many as well when we covered it in our lessons this year. And this lesson is all about making a pure salt. Just a quick revision. Salt's amazing as a chemical. You know, it's rock salt we use in the UK when it's very wintry. We use it with sand to grit the roads. And you know, when it's wintry, the salt actually acts as a chemical that melts the ice. It actually changes the melting point of ice. It lowers it because it acts as an impurity. So on those cold wintry nights, you don't actually have surface water changing to ice and being a hazard for all of the commuters that need to travel to work in the next day. So salt, and we also use salt in our foods as well. It's used in industry as a starting material for other chemicals, for example, detergents and bleaches. You know, it's the chlorine in there that's really important. And the sodium hydroxide finally is a very important part of soap manufacture. Without sodium hydroxide, we could not manufacture soap, and soap's vital and our use of soap is vital in our current fight against the pandemic COVID. So very much in the news. So I do like salt. I don't like eating too much, 2 grams for an adult, but I do like salt. And for all these purposes, we do need to look at how pure salt needs to be. Now, the skills of a good chemist is to be able to achieve a pure sample of salt, and that's essential knowledge as well. So in reference to what we have covered in class, we went through a method, and I got you to write a method in class on how to synthesize a pure sample of copper sulfate salt, and that's what I'm going to be going through today. So regular salt, yes, there you go, that's the picture of it. And in the lab, we can make samples of salts. Now, in the laboratory, we refer to any compound that has a metal and a non-metal part that is a product of a reaction with between an acid and could be a metal oxide, it could be metal, it could be a metal carbonate. We call that a salt, okay? So any acid reactions we've met in the previous videos that I've just made on the playlist would be suitable. But if we're making a pure sample of salt crystals, our priorities change. What we have to do is we have to make sure that we look at all possible sources of impurities and make sure that within our method we end up with something that is just the sample of salt, just the crystals, okay? So the laboratory technique that we followed within the classroom and the laboratory technique that I'm going to summarize with you allows you to make a pure sample of copper sulfate salt crystals, okay? Copper is an exciting one because although copper is not in group 1, group 2, it doesn't actually make colorless salts, salt as in the colorless salt that you're used to seeing in your kitchen. We say colourless, but they appear to be white when they're in a collection. But if you look at an individual crystal, they do look colourless. If you just have a look at the picture over here. So if you have an individual crystal, you can actually see through it. So it does have, it is colourless. However, when you have all of these edges close together, the light doesn't come through so well. So it becomes opaque. So copper is in the middle block of metals on the periodic table. It can form coloured salts in solution. So here is your really important equation. And this is the equation. This is the equation for the reaction that we are going to be looking at right now. Copper oxide, it's a base, it's insoluble, copper oxide, okay? Notice the small u there, the big capital O there. So copper oxide, this is the word equation at the top, and you've got the balance symbol chemical equation at the bottom, okay? You should know what these state symbols are. AQ is soluble in water, and it's dissolved in water. Sulfuric acid with the spelling of F there, sulfate with the spelling of the F there. So sulfuric acid, remember from a previous video, it makes sulfates. The metal is the copper, that's what's present. The copper will combine with the sulfate, part of sulfuric acid to form copper sulfate. In our previous lesson, we talked about acids as well. So the sulfuric acid is a source of 2 protons, 2 hydrogen ions, and those two combined with every 1 oxygen, and that's how you get your water. Remember, final point about this is that you've got L as a liquid. So first step, what we actually find is that we find compounds like copper oxide as insoluble bases, and we actually utilize that, because what we want to do is we want to have a clump of copper oxide reacting with some sulfuric acid. Now we do have to have some fairly high concentrations of sulfuric acid because we want to make a lot of copper sulfate. Okay, if we don't have enough sulfuric acid, we don't have the sulfates to make copper sulfate. Okay, but having said that, what we also want to do is we want to be able to separate out and remove or exclude any remaining sulfuric acid. Why? Because we just want copper sulfate on its own. Okay, so what we do is we have lots of this, what we call an excess, and we add it to a certain amount of sulfuric acid. So here we are, right? And what we can also do is we can raise the temperature. Now we've done rates of reaction, so you know that the temperature increases the stored kinetic energy of all the particles that are moving around in the sulfuric acid. That means they are more likely to collide successfully and react in the time that we give them. So we want them to react quite well, and we also want to boost the concentration of the copper sulfate, and the way to do that is to allow it to dissolve in a higher temperature solution. So here we go. We add the copper sulfate. We keep adding, slowly adding the copper sulfate to the sulfuric acid sample that we've got until no more reacts. So if it reacts, it goes in there, you form that blue solution. Okay, the blue solution forms because you've got copper sulfate in there. Okay, if you add more copper oxide, you find that it reacts further, and you keep adding it, and what happens is, slowly but surely, the rate of reaction decreases, and less and less, it takes more and more time for the same quantity of copper oxide, and you find eventually that the amount that will react every single time you add is less and less, and then eventually you get unreacted copper oxide. That unreacted copper oxide means that all of the acid has been used up. If there was acid there, it would react with the copper oxide. When you do this experimentally, you keep adding it until you get to a certain point where that unreacted copper oxide is at the bottom. Can you remember why it's settling at the bottom? Why it's a solid? Well, the reason why is because it's an insoluble base. Okay, remember what a base is? A base neutralizes acids. Okay, so you keep adding the base, it neutralizes the acid, eventually you get rid of the acid. There's no acid in there, we know that, because it's unreacted copper oxide that remains at the bottom. So we've got, what three things have we got here, and what have we not got? We have got the copper oxide there, okay, because it's at the bottom, right? We've got copper sulfate, see that, because it's blue. We've got some water. Well, that joins the rest of the water that was diluting the acid. Do we have the acid? The answer is no. Of course we don't have the acid, all right? We don't have the acid. If the acid was there, then you wouldn't have unreacted copper oxide. See, it makes sense, okay? So, a couple of things. We want to make copper sulfate, okay? The acid must be sulfuric acid because sulfuric acid gives sulfate salts. In order to react with an insoluble copper compound, we must use a base, copper oxide, and we use that base because what we then want to do is we want to be able to separate the copper oxide. That's what happens in the next stage. I'm just going to go through that. To speed the reaction up, we heat it. We add the copper oxide slowly to the hot acid until no more reacts. Okay, and we can see that because copper oxide is black. Okay, we see it at the bottom of the beaker. And then what we must do as well is we must take care. When we did this reaction, we were wearing safety goggles instead of glasses to make sure that none of that acid popped up through the sides of our glasses. No, we can't wear glasses. Glasses don't provide you the protection. I always say that to students who wear glasses when they do the experiments with me, but now we don't do that. Okay. Step 2 now. So we've got this black powder. Now what we want to do is we want to separate out this black powder. If we separate it out, all we will be left with is copper sulfate and water. Okay? All right, so it's like a little puzzle. We use filtration because the unreacted copper oxide is insoluble. The copper sulfate, however, is soluble. So now we've got copper sulfate in there. It's diluted in the water. It's separated out. It's dissociated. And we have water. So we've got copper sulfate and water. The next stage is to separate out the water. Okay, so what we can do is we can get our sample and we can slowly and with control heat it using an evaporating dish here. It's called a basin, evaporating basin as well. And if we heat it, then we can start to remove some of the water. The water evaporates. But we don't just want to have copper sulfate solid. We want to have copper sulfate crystals because the crystals look beautiful. And the copper sulfate does need a little amount of water. The water helps bind the copper sulfate into these beautiful patterns that we see in the crystals. So what we do not do is we heat it and heat it and heat it and heat it until it's dry. What we do, however, is we reduce the amount of water until you get to a stage where you see some of the little solids on the surroundings. And the reason why you get solids on the surroundings is because you're driving off the water, so you're forming a saturated solution. Okay, and a saturated solution means that you're at the maximum point where your copper sulfate can no longer dissolve any more copper sulfate. Okay, so as soon as you see little crystals forming, that's when you stop. Now, if you can do that, you let it form, you let the crystals form, keep it in a warm place, let the rest of the water evaporate. Usually it's overnight. You'll start to see crystals forming within an hour, but overnight you then see that the rest of the water evaporates, and then you have these copper sulfate crystals. And if you have a little bit of water left over, then you can use a pair of tweezers, take them out, and you can put them on a paper towel. You can dry the crystals and make sure that they're not wet, and you then have pure copper sulfate crystals. That's what we were looking at. It's all because the water particles here become steam and water vapor, and they leave the dish. Okay, so the copper ions that are left behind, the sulfate ions which are left behind, they combine together and they make this pure copper sulfate. Does it have copper oxide in? No, that was separated out in the filtration. Does it have acid in? No, because all of the acid was used up. Okay, so overall, the most common impurities in there would be unreacted substances, but in this neutralization reaction, we actually get rid of all of the other chemicals that are there to get this these pure crystals. Okay, right, a couple of questions to finish off. Just test your understanding. Okay, let's think about some of these questions and some of the answers that could come about. Why does the acid have to be hot in step 1? Pause the video, think about it. It has to be hot because the copper sulfate needs to form a saturated solution. So we want to try and dissolve as much copper sulfate in the solution as possible. Question number 2. Why does some black copper oxide fall to the bottom of the beaker in step 1? Why does it fall? Pause the video. The reason why is because it is an insoluble base, so it settles at the bottom. How does using an insoluble base such as copper oxide help make the pure salt sample? Pause the video. Well, it allows us to separate any unreacted copper oxide. Okay. Why would the colour of the resulting solution start as colourless, become very pale blue, and then become a deeper blue as oxide is added? Pause the video. Well, as you're adding more and more copper oxide, you are introducing more and more positively charged copper ions into the solution. The more of those copper ions that are there, the more blue your solution is. Let's think about question number 5. Explain some of the changes you would expect to see if this method was followed using the insoluble magnesium carbonate. Can you remember what was over here? Try and formulate an answer. Pause the video. The reason why is because all salts made from group 1 and group 2 are colourless. So that would mean to say the changes you would see is you would not see blue crystals, you would see colourless crystals. Shame on you if you said white crystals. Colourless crystals. Okay, year 8s, best of luck. That's another video in the bag. If you've done all 4 videos, that means you're through half your revision. That's a fantastic achievement. Keep going. You're going to do the other 4 videos as well. Take care. Stay safe. Bye for now.